Hey folks, how's it going? This is Mr. Murray coming to you with a due now for 3/24/2020 for Course 1 CP. Okay, so in this video we're going to again provide another example of function analysis. This is going to be very similar to the worksheet that you hopefully started yesterday, March 23rd's lesson, and will complete today. And so what I want you to do in this video is, as with yesterday, and if you haven't seen yesterday's video, I would encourage you to do that. It's linked to in the class Google Doc. I want you to, given this graph here, find the following information: the domain, the range, the axis of symmetry, the vertex, any x-intercepts, the y-intercepts, and any transformations from the parent function f of x equals x squared. Okay, just to clarify, you can assume that there are arrows on the ends. I'll put that there just to be clear. So what I want you to do is pause the video, try to find these 7 items, and then when you're ready, unpause, and I will show you how to find them. All right, so here we go. First, I want to find the domain. So hopefully by this point, we've caught on to the fact that the domain is negative infinity to infinity. Again, as I explained last time, and I'll explain again, there's no breaks in the graph. We can see it's a continuous graph. I can trace it with my finger. This little thing here, I don't know what that means. I'm assuming that's just how they point out the vertex. So the domain is everything. Okay. And as a student brought up the other day, I believe, and like, well, you did give us this one time where the domain wasn't everything, but you can clearly see if there are arrows on both ends. In that example, that was actually not the case. So it does require a little bit of thinking and examining. But generally, in almost every single case, especially when there's arrows on the end, you are going to have a domain of negative infinity to infinity. And those are really the more interesting functions, with few exceptions. Okay, the range, notice this one points down. Okay, so we can see that the highest it goes, let's call that 16. That's the highest that the y values go. And because it points down, I put my negative infinity on the left. So you have to think about it. Is there a highest it goes or a lowest it goes? If there's a highest it goes, the number goes on the right with a negative infinity on the left. And if it's a lowest, that goes on the left with a positive infinity on the right. And that's something we'll continue to work at. All right, axis of symmetry. Well, it appears, and I'll do the vertex again first. The vertex is 4, 16, making the axis of symmetry x equals 4. This checks what we know, because we know that the axis of symmetry always goes through the vertex. It is an x equals because it's a straight up and down line. And to go through the vertex, well, the vertex, since we know it's 4, 16, to go through 4, it has to specifically be x equals 4. All right. Again, notice that the x of the vertex is the same as the axis of symmetry. The y of the vertex shows up in the range. That is a good sign. All right, x-intercepts. This one's an interesting one. So 0, 0 is an x-intercept because it touches the x-axis here. And 8, 0 is another x-intercept. And if you think about it, this makes sense based on the symmetry. 0 and 8 have the same y value. So the vertex of 4 must be right in the middle. Okay, so that's a way to, and when we get to the next form we're going to do, intercept form, we want to think about that way of going both ways. If you have the vertex and you have 2 points that are the same distance from the vertex, their y has to be the same. But on the other hand, if you have 2 x's whose y's are the same, you also know that the x of the vertex is right in the middle of those x values, right? So in this case, 4 is directly in the middle of 0 and 8. So that actually would let me, if I knew 2 points whose y values were the same, work backward and find the x of the vertex, potentially making it even easier than with standard form, depending on the situation. The y-intercept is also 0, 0. Sometimes it just works out that way, but we can see it touches the y-axis here. And transformations in the parent function. So to me, I'm not seeing any definitive signs that there's any stretching or shrinking. It still appears to be the same shape. So I'm going to say, well, it's going to have to be a reflection over the y-axis or horizontal axis. I'll take either one. And I'm sorry, that's not a y-axis. That's an x-axis. You'd be surprised. See, even I do that, how often that happens. Okay? Then I'm going to do a translation. I'm going to move right by 4 and up by 16 to get from a vertex of 0, 0 to get to a vertex of 4, 16. Okay? So the reflection points it down. The translation shifts the vertexes around. And so we could confirm that the A value is still 1. And so what I did is I actually was able to confirm that just now using what I know about quadratics, but it's okay if you don't. All right, so hopefully this made sense to you. Please make sure that if there was anything about this that you're still working through, that you just go back and take a look so you understand. But what we're going to do today is we're going to continue to work on the analysis, now recapping vertex form, go nice and slow and kind of make sure we really understand before moving on. All right, so keep up the good work. Don't forget to love math, and remember, you can do it. All right, thanks for watching. Best of luck with today's lesson, and I'll see you next time.